fact that the wave function for matter can serve as a probability density also opens up a new possibility for us. Whenever we have a continuous probability distribution of the sort that a wave function might represent, we're able to write down average values for different quantities by simply using that continuous distribution. So for example, if our probability density has the function rho of x, and we'll just say that that probability density then has to be multiplied by an increment in x to make it a real probability, then we can write an average value for some quantity as simply the integral over all the values that x could have, so we'll just say minus infinity to infinity of that function times the probability density dx. And this would give us an average value because in essence we're weighting each value of a of x by the probability density that the system is at that particular location. Then we sum over all of the possible possibilities. Now, how would we apply this in the case of a wave function? Well, we've seen that in fact our wave function enables us to measure certain things through the use of operators. So for example, the Schrödinger equation is something that allows us to measure the energy of a system, because if we have an eigenfunction of the Hamiltonian, we would get the energy value out as a direct result of making this operation. So let's expand this a little bit, and noting that the probability density for a quantum wave function would be given by the square magnitude of that wave function. So it would be this entity. That means that we need both a factor of psi complex conjugate and of psi itself. But how do we split these two versions of psi when we're dealing with the average value of something else? Well, I'm going to use the Schrödinger equation as an exemplar for this, and then we'll get into how we might do it more generally. So from the Schrödinger equation, we have this expression. Now, if I were to multiply on the left-hand side of the Schrödinger equation by our complex conjugate of the wave function, I would end up with a relationship that looks something like this. And I realize this looks like a kind of a strange object here. We've taken an operation of the Hamiltonian operator on a wave function and then multiplied it by the complex conjugate of that wave function. But now this must equal, again, this assortment here. The complex conjugate of the wave function times the energy times the wave function. Now, energy in this case doesn't perform any operation, it's just a number, so we can actually bring it out front, and we end up with this double set of wave function, its complex conjugate and the wave function. So that's basically E times this probability density squared. Now, if I were to take both sides of this equation, so this piece and this piece, and integrate them over all the space that the wave function covers, I would have a result that looks something like this. And that would be equal to my energy times this integral over all space of my probability density. Okay, now we've shown that when we normalize this wave function it's 1, but I'm going to leave it separate for now. And because I haven't necessarily specified a wave function, I'm going to further make the assumption that this is giving me some sort of measure of the average energy over this wave function. But I still have this factor on the side. So now I can take this and solve for this average energy, and when I do that I'll end up with this result. I'll have the average energy would be equal to this integral over all space of psi star x Hamiltonian operator psi of x dx divided by the integral over all space of psi of x star psi of x dx. And it turns out that this, while I've been kind of ad hoc in my development of this expression, this in fact leads us basically to a postulated notion that the expectation value of some property A in matter wave would be given by an expression very similar to this, where we would write, instead of the Hamiltonian operator, would be the operator corresponding to that property A. And we would then divide by the overlap integral of a wave function with itself. So in other words, the square magnitude of the wave function integrated over all space. Now I've mentioned that when we have a normalized wave function, so if it's normalized, then these expressions simplify somewhat, and we would have that the average value of some property A would just be the integral over the psi star with the A operator in between and psi dx. But the important point is the structure of this integrand, that we've sandwiched the operator in between the complex conjugate of the wave function and the wave function itself. The operator is only operating on the right-hand wave function, but this whole thing is what gives us something akin to this expression that we've written up here. That's really a classical continuous probability distribution for a system. Now, I'm using a lot of big fancy language here, and I apologize that maybe it doesn't seem so clear. But the real, I guess, essence of all of this is that we want to define this expression as equivalent, or perhaps even better, this expression as equivalent to the expectation value of a given property. And so in this case, a given property A over the wave function psi of x. Okay, so it's specific to this wave function. That's why we're using that wave function in there.